Hello, everyone. Can you hear me? Okay. Do you think we should start? Thank you all for coming, despite the drizzle and, and the cold. Today we have our second Atlas lecture, and we have Alex Knodell as a speaker. I will give a small introduction, which I know is not needed, but it's a custom. So Dr. Knodell is Associate Professor of Classics and Director of the Archaeology Program at Carleton College in Minnesota. In Greece, he's currently a research affiliate at the Norwegian Institute and a Senior Associate Member at the American School of Classical Studies at Athens. He co-directs the Small Cycladic Islands project and previously co-directed the Mazi archaeological project in northwest Attica. His research focuses on landscape, interaction, and long-term social change, which are core themes in his recent book, Societies in Transition in Early Greece, An Archaeological History. So I think we can give the floor to Alex, and thank you.
Thank you, Tina, and thank you, everyone, for coming. Can you hear me okay with microphones? Okay. Should I talk louder, or well, we'll see how it goes. Just cover your ears if it gets too loud. Well, thanks first of all to Tina and for the other organizer and to the other organizers of the Atlas seminar. I'm very, very happy to be here. I was sorry to miss the first one in this series, but I'll try to follow the rest of them as we go forward. I should also note from the beginning the collaborative nature of this work. Some of it draws on work with my colleagues from the Effort of Antiquities and from the Norwegian Institute with the Small Cycladic Islands project. And we'll hear about individual contributions as we go on. But I want to mention from the outset, especially those who have contributed to the remote sensing part of the program, namely Tom Garrison on LiDAR analysis, along with Rosie Campbell, and on anything drone-related, aerial photography, photogrammetry, etc. That's mostly been the contributions of Hussein Ozturk and Evan Levine. So I thank them all warmly. And we'll note other people as we go along. The general plan for today is to start with a little bit of a historical introduction of remote sensing in archaeology, mostly because I think that this is interesting intrinsically, but also from a more practical perspective, the work that we're doing on the Cyclades is drawing a lot on paradigms from elsewhere in the world, especially developments in LiDAR use in archaeology that have happened in Mesoamerica. And so by looking to other parts of the world and to kind of the history of the discipline, we can find some opportunities for applications of similar methods, I think, in Greece. After that sort of introduction, which also contains some, fun facts about hot air balloons and things like that, we'll move into the specific work of the Small Cycladic Islands project, in particular the work that we're doing with remote sensing, mostly with LiDAR analysis, but also and especially using multiple methods to investigate multiple scales. We'll move from the kind of big picture of the field project to a case study from Paliagos, and then at the end we'll talk about how we scale this up into bigger picture research questions and where we're going from here. There's a lot of remote sensing data we've collected from many different places in the Cyclades. Not only the small islands we're investigating with the Small Cycladic Islands project, but also larger uninhabited islands. And we want to start kind of putting this together to develop some big picture regional perspectives. So from a remote sensing perspective, we'll start with the basics of aerial photography and then get into things like satellite imagery analysis and 3D imaging, and then get into questions, especially future questions and future research agendas related to machine learning and some of the more detailed spatial analysis we'll be doing. In general, by remote sensing, at least in the context of this talk, I'm talking about this type of stuff, sort of looking from the air and especially imaging from the air. But we might also include various types of geophysical survey in this category as well. So the first of our fun facts, aerial photography and archaeology goes back quite a ways. Aerial photography in general originated in 1858 using balloons. And these balloons, interestingly, were already in use for military surveillance before they started taking pictures from them. First balloon photography in archaeology was images of Stonehenge and the Forum Romanum from the very end of the 19th century and beginning of the 20th century. And then these techniques were being used especially to investigate things like irrigation patterns in the Middle East and difficult to explore jungle environments in Mesoamerica. And one thing I want to note from the beginning is that remote sensing in archaeology, like in many disciplines, is highly interlinked with other surveillance technologies that have military applications. Archaeology, I think we all know, is one of these sort of disciplines that grabs on from innovations in other fields. And this can be very useful, but also we should think about where this technology is coming from and what it's really meant to be used for. The first aerial flights that had particularly archaeological applications occurred in the 1920s and 30s, and one of the main areas where people were using these new technologies was in Mesoamerica, where A.V. Kidder and Charles Lindbergh were involved in saying things, and I quote now, above all things, we wanted to get an idea of what the Maya country really looks like, for in spite of the fact that archaeologists have for many years been pushing their way into that region, they've been so buried in the welter of forest, their outlook has been so stifled by mere weight of vegetation that it has been impossible to gain a comprehensive understanding of the real nature of this territory, once occupied by America's most brilliant native civilization, as they were describing it. So two things that are important to highlight here from this quote is, number one, the difficulties that vegetation presents date back to the earliest ventures in aerial archaeology of any kind. And two, I think it's important to know that remote sensors in archaeology are often field surveyors first, as opposed to lab technicians. We're motivated mainly by our frustrations in the field to find more efficient paths to discovery. And while in the Mediterranean region we don't have quite the same problems or quite the same scale of difficulty with vegetation that people do in the Maya area, we still encounter some similar frustrations nonetheless. So these first flights were then applied in settlement pattern research, especially in places like Tikal in Guatemala and the Copan Valley in Honduras. And they were used on the one hand to map the presence of sites or settlements that you can see from the air, of course, but also in larger scale mapping, most significantly through stereoscopy. So overlaying different aerial photos taken from different angles and using this to create essentially a proto 3D model of the landscape. So it's very important for topographic mapping as well as for noting the location of archaeological sites. And this is, again, a theme that endures to the present day. Now, aerial photography and archaeology today looks a little different. On the one hand, it's a much smaller scale, at least in terms of the types of machines that we're using, but on the other hand, it's nearly ubiquitous. Basically every project that I know of, whether it's a survey or an excavation, makes use of drone photography in some way or another, ranging from simple trench photographs to aerial photogrammetry, sometimes at the scale of individual sites, but individual trenches, but also going up in scale to sites or landscapes. I think with drones anyway, obviously they're ubiquitous and obviously they're very, very useful for a number of different purposes, and we'll see some of them in a moment. But the kind of greatest potential for use of drones in aerial photography and archaeology has to do with larger scale investigations, and then how we can push this into new types of research questions and new applications using different types of spatial analysis. We've got a little... As I was saying, I think that the most exciting applications of the use of drones in aerial photography and archaeology have to do with some innovative work that is trying to basically ask new questions of the data that can be gathered with the sensors. And we'll look at a couple of examples of that in a moment. At a much more basic level, some of the work that we've been doing on SCIP involves the generation of orthophotos, a high-resolution orthophoto from a mosaic of images used to create a DEM on the one hand, but also just to look at the imagery in high resolution. And this allows us to do things like, well, detailed architectural drawings, a new architectural study, and a plan. And you can see how we went from an earlier plan by Athanasios Vionis in 2012 to our drone-based aerial mapping to a new plan of site that includes several more towers along the east side of the site along here, and also a better understanding of the entire circuit of the fortress at Vriokastro near Paros. Drones are constantly getting outfitted with new and different sensors. We have multispectral imaging capabilities, a technique used more often in satellite imagery analysis than with drone cameras. And we also have the capacity to use thermal cameras now with the drone. And this is something that's new for us as well. This year we acquired a drone that has both a normal RGB sensor on it as well as a thermal sensor. And that allows us to do, well, a variety of different things, but the most significant of which is the potential to see some near-surface features. We'll talk about that a little bit later when we get to that part of the talk. As to the new and exciting research questions I alluded to before, I want to highlight a couple of recent papers. One of particular interest for survey archaeologists, where Hector Rango and colleagues have discovered that it actually works reasonably well to count sherds by drone. And people were initially skeptical of this, but they've actually done a pretty good job showing how it works. So basically, in place of a field surveyor, you would have a drone going along a survey transect. And as you see in the image on the left, yes, your left, it is you can make out little sherds there. So basically what you're doing is a form of image classification, which is the same principle that will apply at a larger scale. Here we are. So, right, the drone is going along the survey tract just like a person observer would be doing that, and it's recording this simple image. Right? And so what you're doing is an exercise in pattern recognition and machine learning. You train the program to recognize certain signatures in images as pixel combinations, like a combination of the red triangular stuff is a sherd, right? You then highlight these areas by classifying them to stand out, and that is what you see as the yellows in the top middle image. And then you filter out the rest of the material and vectorize the part that's been highlighted in order to create individual vector features that can then be quantified, measured, and classified further. There's also lots of interesting work involving new applications using old data in exciting ways, often by combining multiple data sets and multiple types of data sets. Historical aerial photos, cadastral maps, and then they're doing new processing and overlaying of different types of imagery to identify old patterns of land use, settlement signatures or feature signatures, and so on. This is particularly important because many now invisible or destroyed features can become visible in this way. So there's exciting work going on in this front, including and really especially in Greece. Satellite imagery has been less widely applied for a variety of reasons in Greece, but goes back to the Corona program in the mid-20th century, again, a military program, but that was followed very soon after by the first research satellites using multispectral sensors, the Landsat program. Next generation imagery included, well, all of these commercial companies offering higher resolution imagery. And now, of course, we're in the age of freely available global coverage programs like Google Earth, Bing Maps, etc. And at the same time, we have a whole suite of commercial providers of multispectral imagery, digital elevation models, and so on. And this highlights also that satellite imagery is not useful only for what you're looking at, for the photographic image itself, but also for creating secondary products like digital elevation models for spatial analysis. Something big happened around the turn of the millennium, this sort of resolution revolution, as we went from Landsat images with about 30-meter resolution to 1-meter resolution images. And this example from the jungle in Guatemala highlights this quite well, where originally you see this blob, and in the sharper image, of course, you can make out individual buildings and the layout of the entire site. But even without that level of detail, these blobs can be very, very meaningful to an analyst. In this sample from Guatemala, even where there were vegetation signatures, or even when there's vegetation coverage, you can interpret these vegetation signatures that are associated with particular settlements in order to identify sites. And that's what we have here in a main region of the Maya area, where a particular settlement signature or vegetation signature for settlement was used to identify multiple sites and complexes that would be invisible by normal aerial photography. And there's still more to be checked and tested. Machine application learnings there, well, on the front of satellite imagery analysis, have been used to identify features, especially mound identification in the Kholistan Desert in Pakistan, and remains from the Indus Valley civilization. So this works with the same basic principle that the sherd identification by drone worked before, where you are kind of looking for patterns and then you are training a program to recognize those patterns. In one case it was sherds, in this case it's mounds in satellite imagery. The thing I want to touch on last is the importance of elevation data, and some advances were made using radar for elevation scanning of entire landscapes. But most people are still using satellite imagery for this. At least satellite imagery is freely available from various vendors for much of the, well, in fact, all of the world's surface. So this allows for some site discovery on the one hand, again by identifying similar signatures in the elevation data. And then these signatures can be ground truthed and oftentimes more detailed remains of platforms or structures can be mapped out. And I showed this to highlight the importance of ground truthing, where obviously imagery is useful in site identification, but is not going to tell you everything that you want to know. Let's skip over this. So resolution matters here, and LiDAR made a big difference with this. It was a game changer, and I've told you all of this about Mesoamerican archaeology because these are where a lot of the remote sensing innovations were happening, especially to deal with that very difficult environment and difficult vegetation coverage. So LiDAR has been around for a while. stands for light detection and ranging, and we don't have to capitalize it weirdly anymore because it's like radar. It's pretty commonplace these days. You can just use it as a word. And unlike other surveillance technologies, it was not developed originally for military purposes, but for meteorology, tracking clouds in the 1960s and 70s. Now, it didn't take long for archaeologists to think that this might be useful for them, and there were some early archaeological applications in the 90s and 2000s, but they didn't really start to become successful until a multi-beam sensor started being used. When you see this illustrated here on the left, where the sensor is basically shooting multiple beams at the same time, measuring the reflection back, and this allows for basically different angles of data to be collected as you're going. And LiDAR, of course, is unique in its capacity to penetrate vegetation, which was very useful in jungle environments. Probably the most famous case study comes from Caracal. And you can note how the LiDAR data renders the pyramid in the center of the complex, and then this is an aerial photograph from about the same angle. And it's pretty spot on. Now, LiDAR has been used mostly, including in Mesoamerica, at the scale of individual sites, but gradually projects have begun to scale this up to hinterland surrounding sites, and also into doing regional comparison, as we see with this Pakunam LiDAR initiative, where they've collected basically more LiDAR data across Mesoamerica than all of the previous projects combined. And that's with this explicitly interregional and comparative goal in mind. The use of comparative data sets allows also to draw things like chronology out of different signatures in the data. So here's illustrated, one signature that by comparison they found is associated with pre-classic mound groups, this melt signature, versus the sharper edges of classic period sites. Now, we're not there yet in the Mediterranean, but this is where we could be heading. LiDAR use in Mediterranean archaeology is less widespread, but increasing, especially because of its public accessibility in several countries, public accessibility or at least wide availability in many countries. Unfortunately, Greece is not one of them, but maybe it's coming. There have also been large-scale identification projects in Lebanon and using Italian hill forts, whereas applications in Greece have tended to be more site-specific, with the exception of two recent projects, one in central Euboea and the other with my project in the Cyclades. But if you want to read about these site-specific projects, you can find this work in the work of Thierry Lucas and Jesus Garcia Sanchez in the recent publication noted here, and also of this other recent publication of Agapiu, Decoury Hild, and colleagues about Aphidna. So there you can see very clearly that there is vegetation coverage, and even though the vegetation is quite thin, it makes a big difference because when you peel it away, you see very, very clearly the grid and plan of the entire site. Work in Euboea and the Cyclades. I'm involved with the Euboea project, but our goal there is to scale this up from the individual site and to move into really regional scale analysis. So much of what I'll be talking about as we go forward is in explicit relation to the Small Cycladic Islands project, but it's also kind of a wider and more comparative project that involves areas that we won't be surveying with SCIP. So SCIP is a collaboration between the effort of Antiquities of the Cyclades, the Norwegian Institute at Athens, and Carleton College, and it's directed by Dimitris Athanasoulis, myself, and Zarko Tankovic. as you can see, we're working in many different parts of the Cyclades, in fact, across the entirety of the Cyclades. In 2019, 2020, we started around Paros and Andiparos, then moved into the western Cyclades and Syros, and this past year we were working in the Kymilos Milos island group. In the future, well, this coming summer, we'll move to Andros, Tinos, Mykonos, and Andros, and then finish up with the small Cyclades and Santorini and Anafi in 2024. That's the plan, anyway. At the end, the idea is that we'll have surveyed about 100 islets, most of which are well under a square kilometer in size. Some are a little bigger, but we're also including LiDAR-only surveys of larger islands that we would never be able to deploy the person power to survey in their entirety. So the project was motivated by several questions. One is that this is a unique type of microenvironment, and we're simply asking what roles do small islands play in their regional contexts. We hear about isles of refuge in the archaeological literature and in literary sources. So islands as places of retreat, as strongholds, and occasionally as pirate hideaways or places of exile. We also hear about them as destinations, stepping stones in larger sea routes, ports of trade, locations of sanctuary, and also places for resource extraction, mining, keeping goats, or just doing agriculture. So all of the islands in the study area are currently uninhabited. Most are very, very small. Some are well under 1 square kilometer. Some are a little bit bigger than a square kilometer. And one that we've surveyed so far is 18 square kilometers. That's Poliagos, which we'll focus mostly on today. Some of these islands can be described as offshore or nearshore islands, meaning they're very close and function as satellites to larger landforms. And some are more isolated and would fall into the kind of stepping stone category. These ones out here, not so much satellites, but on the way to other places. So to just run you through our field seasons very briefly, to show you where some of these places are. For more information on the first couple of seasons, we published a couple articles about that in Journal of Island Coastal Archaeology and Antiquities Project Gallery. 2021, Western Cyclades and Syros. This past year, with the little dots, and then Big Poliagos, where we spent most of our time. And then our plans for the future, which I've somehow left one out of. Okay, so for our larger study, including also LiDAR analysis of larger uninhabited islands, a key research question are how do things like landscape boundedness, size, and environmental diversity affect the long-term history of occupation in these places? And are there thresholds that exist for size, for example, that either facilitate or inhibit specific types of activities? Finally, do these apply at some points in history, but not in others? Our goals then are to determine, on the one hand, the long-term occupational history of these places, many different places independently, to describe their recent landscape evolution in collaboration with our geomorphologist colleagues, and then to assess things like size, resource base, relative marginality, and connectivity for each island. And finally, we want to put all that together to try to understand long-term socio-environmental dynamics in Cycladic small island environments by comparing them both within the project area and to other small islets elsewhere in the world. In terms of how this plays out on the ground, our methods are pretty traditional in this form of a pedestrian survey. We have a team of five field walkers walking side by side across the landscape while collecting and counting artifacts as they go. At the same time, feature documentation specialists work on the architecture through a variety of, again, traditional and newer methods. Basic mapping with DGPS, sometimes mapping with drones, aerial photography and photogrammetry, but also quite a bit of old-fashioned sketching and architectural drawing. In areas of particular interest, we aim to supplement the field walking collections with more detailed site-based gridded collection. And you can see here in this illustration the sherds that were picked up in the initial field walking collection versus a much more detailed site gridded collection in black. We carry this out in areas where we think there's a lot to be gained by more detailed analysis of the pottery to extract functional and chronological information. Lithics analysis is headed up by John Cherry, while the ceramics analysis for the project is headed by Denitsa Neneva. And obviously this allows us to kind of isolate different periods and functional areas and create nice little maps like this that show the development of an islet from the early Bronze Age into the modern period with a big boom in geometric to archaic times. At a larger scale, we can compare general densities, for example, between Paligos and other small islets surveyed in 2022. And then we can also plug in chronological information for the data set as a whole. So that's a sort of overview of our data set that's contributing to research goal number one, trying to get a sense of the basic landscape history and history of land use in these places. On the remote sensing front, we're using a combination of different things to address different scales. So drone-based aerial photography is well suited to investigating features, sites, and even small landscapes like small islands. But if you're talking about larger areas, it's tough to cover 18 kilometers with a drone, at least the drones that we have. And finally, aerial thermography can be very useful in very targeted places, mainly sites and particular features. So, in our remote sensing checklist, we need good quality DEMs for spatial analysis, satellite imagery in which buildings and large-scale features are visible. Those are all freely available. High-quality aerial photos, we collect those during field work, but we're left with questions like, what about the vegetation? And what about interpolation and extrapolation from this? And that's how we came to this LiDAR acquisition, which we commissioned from Aerophoto, a Thessaloniki-based company, in May. So that's another thing that's worth highlighting is anything related to LiDAR is still pretty new in terms of our analysis. I'll show you the results that happened in tandem with our initial field season, especially around Paligos, but much of the rest is kind of a project that's just in its very early phases. The goals of the LiDAR program were to supplement and expand our knowledge of areas already surveyed, and this is important. So we collected data also over areas that we had previously surveyed in quite a bit of detail, because much of that area is still obscured by vegetation. We also want to investigate islets that are already well published and have been surveyed by other projects and are currently being surveyed by other projects using other methods. Now the goal here is to use this to create training data sets for a more basically detailed analysis or more automated analysis and to know what we're looking at. As a precursor to our own survey work, we also wanted to be able to look at this imagery in advance, and that's most of what we've done up to this point. And then finally, we want to investigate areas where we're not able to carry out pedestrian survey due to issues of accessibility, size, or other constraints. So training data from the places that we know there are features can help us to start recognize patterns and then that can be applied ideally in cases where we won't be able to go ground truth them. Maybe someone in the future can go ground truth them. In terms of the specs on this data set, we've put some statistics here at the bottom. Basically, it was a complicated flight plan involving about 68 strips of collection. While only 84 square kilometers of land were covered by the LiDAR data, the aircraft are covering strips of about 415 square kilometers. And that's because there needs to be a lot of back and forth and overlap in order to triangulate the data sets. More interesting, perhaps, is the next phase and the different types of data that we're getting from aerophoto. The raw data is a point cloud, so the sensor is shooting millions of points that are reflected back, but then these points need to be classified. They can be classified to recognize things like the ground surface, to recognize architecture, and vegetation. And it does that by algorithms that read the sort of difference between one point and another group of points. So for example, if a bunch of points are getting stuck in a bush, and then a bunch of other ones are on the ground, an algorithm will recognize that signature, and then you can classify out the vegetation. So point cloud data is the raw data that's used to generate two different types of surface models. In the first place, a digital surface model, which is everything, including vegetation, walls, etc., and then a digital terrain model, which is sometimes called a bare earth model. The next step after that is to create visualizations that are useful for archaeological purposes. So you have your DEM on the one hand, in the upper left, this DSM, and then you can run these data through different types of visualization software. Through mainly what we're using is something called the Relief Visualization Toolkit, which is available as a plugin from ArcGIS and QGIS. And this highlights, obviously, different characteristics. One that we found particularly useful and that we used quite a lot is something called a red relief image map. Red relief image map combines basically positive and negative openness with a red-colored slope model laid over the top. And this has been proven very useful for highlighting archaeological features, especially in the Maya area, but was also useful for us on Paliagos. Even when you settle on a visualization that you like, though, you really need to be looking at different data sets simultaneously, or at least back to back, because they highlight different things. The DTM shows things like terraces and hydraulic features especially well, especially things that are obscured by vegetation, some terraces and hydraulic features there. A DSM will show modern constructions quite clearly. And you can combine things like a DSM or a DTM and orthophotos to, highlight different characteristics. These tend to show modern walls and buildings very well also. So in terms of combined visualizations, we could see this right away in islands that we had surveyed in previous years in 2021 and 2020. So here's an example from Kitriani. One of the main sites on the island is this church complex you can make out here, even in the point cloud data. You can see in blue lines here where we mapped archaeological features when we surveyed the island in 2021. And based on the satellite image map, you can sort of see that there's some other stuff going along in the area. But it's only when you peel away the vegetation that you end up with a very, very clear picture of a human-modified landscape. And this is not only in the vicinity of the church on Kitriani, but also it goes around and occupies, in fact, much of the island. This is stuff that was missed by field surveyors, not because they did a bad job, but just you can't see these things on the ground when they're there as clearly as you can in this type of high-resolution imagery. Similar situation on Strongy Low, which we surveyed in 2020. We noted there an extensive system of terraces, and in fact we mapped an extensive system of terraces both through on-the-ground methods and using photogrammetry collected by photogrammetric data from drone-collected imagery. But even with that, you see that these terrace systems are, again, much more extensive, wrapping around here, and it included also areas where, we didn't have a clue there was anything going on. So, it's good for basically checking your work on that front. It's also very good for pre-field analysis, and you see different things in the LiDAR imagery than you do in the aerial photo, like in this example from Ikria, which we surveyed this past year. So you can make out in the aerial photo some bigger structures with wall remains above the ground, and those are readily apparent in the LiDAR as well. But what you can't make out here is the very, very kind of extensive nature of the building program that went on this small island. And then this is followed up by a next level of analysis on the ground using traditional architectural drawings and aerial photography. So the point here is that it's really part of a larger process for us. I mean, on the one hand, we kind of worked backwards with the LiDAR data, and on the other hand, we're looking forward and trying to fold this into a broader pattern of analysis or broader system of analysis. On Poliagos, this was particularly necessary, mainly because of the size of the island. We approached this by divvying up the space into a 500 meter by 500 meter grid, and this grid squares were then inspected individually by analysts in the lab before field teams went out to ground truth and record more information. An essential part of the in-lab analysis wasn't just identifying features, but also creating classifications for them. So not just something's there, but what do we think it is? So there's a stage of interpretation built into it. Our classification was fairly straightforward because you can't be too specific, but you can distinguish sometimes between things like a normal wall and a terrace wall, or a part of a terrace system. In terrace systems in particular, you can also distinguish between the wall itself and the area that's being made agriculturally viable. Enclosures were another key feature type. So analysis like this was done for each grid square, and then field teams took maps like these into the field in order to ground truth what had been observed in the lab. A key strength of the LiDAR data is in identifying terrace and drainage systems. So the types of features or landscape modifications that create patterns at a landscape scale as opposed to individual walls, let's say, or even small buildings. You can see sort of how extensive these are in some areas of Poliagos anyway. And this also highlights how it gives you a very, very different perspective than you do when you're just on the ground, where you might notice one wall or a couple of walls or know that you're in a system of walls, but not be able to understand its full extent. We were also interested in comparing basically on-the-ground feature detection and LiDAR-based feature detection more explicitly. And that's what you see illustrated in this map. On the left, you have features detected by LiDAR in blue, and features that weren't detected in LiDAR, but that were detected by pedestrian survey in red. And then the image on the right, you have just this different feature types across the entire island. And the other type of feature, in addition to agricultural and hydraulic systems that I want to mention, is roads and pathways. These things really pop in the LiDAR data as well, and are often not easily visible on the ground, especially more subtle ones. So I want to turn for the last bit about the Poliagos survey to one site where we did quite a lot of, well, we invested a lot of energy, both with LiDAR and with traditional field collection, gridded collection, and aerial photography and analysis. So we noted a concentration of Bronze Age pottery in this area, and that is over here at this place called Bernardu in the initial field walking. We also noted some significant chronological patterns here after the fact, where we have earlier Bronze Age material toward the bottom, and then basically a shift happens and we move upward as we get later in the Bronze Age and into the early Iron Age. There are also some subtle differences in the types of features that you see where these terraces are a bit more run down than what you see over here. That may have something to do with the chronology, but it's not a relationship that we're kind of confident in yet. Needs further work. So this area here is what we want to focus on, or what we did focus on for additional field work after the initial identification. It's a place called Bernardu. It's located near the Bay of Myrsini and across from this little islet of Manolonisi, which provides additional protection. Basically, Poliagos is one of the most protected areas in the Milos-Kimolos area in terms of its suitability for ships to harbor and pass the night in basically any weather. The architecture is along the ridge and is mostly low stone walls. A combination of the initial LiDAR analysis and a detailed program of aerial photography allowed us to produce this map in the end of all of the architectural remains, but it was quite a process getting there. As you could see, this was not the image that we had from the LiDAR data alone. We gridded the site as a standard practice and used this grid as a basis for both architectural analysis and field collections. Field collections were also designed to cordon off different rooms, so not just follow the 10 by meter square, but to basically respect boundaries that were built into the architecture. We also carried out aerial thermography at the site in order to see if there were subsurface features that we could detect that were not visible on the ground. And we did this by carrying out a series of flights at different times of day. Basically, thermography relies on detecting heat change, well, differences in heat, right? And so you can compare images from different times of the day when different materials are going to have different heat signatures. So it's good to do this early in the morning or shortly after dusk. And the reason for that is because soil and stone, architectural remains, will cool at different rates. They'll heat and cool at different rates. So by comparing different images, you can sometimes get subsurface features highlighted. So if you look at the red box, that's where we're looking now, where in the UAV photo, you see that basically this building runs into a bush and becomes invisible, and that's also the case from some of these other flights at dawn and at midday. But you can sort of make out the continuation of this obscured wall in this dusk flight. I'll show you also just some of the results of the gridded collection when we divvy things up by period, because this was a big find for us. I mean, obviously I've been focusing on the remote sensing here, but this was a big find in terms of the chronology and the history of the Cyclades, because we do not have too many middle to late Bronze Age sites. and that's exactly what we seem to be dealing with here. So there's some earlier materials of the Final Neolithic and early Bronze Age, and these earliest remains from the early to middle Bronze Age coincide with one small architectural complex up here and this central building complex over here. Obviously, the Middle to Late Bronze Age have the most remains, but already later in the Bronze Age, we start to fade off, and then occupation stops when we reach the early Iron Age. If we scale this up to the island as a whole, we also see that, well, basically people move up as we go forward in time. There's lots of early and middle Bronze Age material close to the coast, and then we have this settlement shift up above the main site, but that also includes a different type of landscape that has different types of features as we move a little bit later in time. And I want to show you that settlement signature in the LiDAR imagery over here, where instead of a terrace settlement, we have things like systems of enclosures. This one here, there is another up here that you can see, and various others that you can make out in different parts of the uplands. Even in the absence of ceramic remains, we can read different patterns of land use from the LiDAR data. One that we see very clearly is in northern Paleogos, where we have a very heavily terraced area on the left, and then there's this ridge, and in fact there's a wall that runs along this ridge with an access point exactly where this goat trail goes. And it's definitely for goats, not for people. So basically what's happening here is they've walled off, literally, the cultivated area from the area that's used for the herds. And that's very clearly visible in this LiDAR data here. And it's for obvious reasons of not wanting your goats to eat your crops. So to wrap up about Paleogos, we, I think, had some success not only in the methodological concern of helping us do our work and identifying areas of interest before we went to survey them on the ground, but also in reading the features that we're seeing in the landscape in the LiDAR data alongside chronological patterns that we're seeing in the pottery. I think this bodes well for future analysis. And I'll finish up now by talking about just some of our next steps. The 2023 and 2024 field seasons, the work that we hope to do on larger uninhabited islands, and then some of the quantitative and comparative questions we have going forward. Finally, we'll look to what applications these data sets might have beyond archaeology. As we said, in 2023 and 2024, we'll be working in these areas and in the southern Cyclades. As to the question of larger inhabited islands, there are two types that we're looking at. On the one hand, areas that have known archaeological records, like Delos, Rhynia, and to a lesser extent, the Spodiko, and islands that are relatively unknown or understudied archaeologically, like Yaros and Adimilos. This has great potential for doing some new mapping and analysis on Delos and Rhynia in collaboration with the effort of Antiquities and the French School at Athens. And many thanks to Zosi Papadopoulou, who has been working with me on this. We can see that already the LiDAR data reveals quite a lot of quantitative things that we could do with, for example, the cemetery of Rhynia, these individual depressions probably corresponding with individual graves, many of which I imagine have not been mapped, even though there has been extensive work in this area. It'll be really exciting to start to put together these data sets. And finally, on Delos, we can distinguish different basically zones of agricultural use and perhaps different chronologies based on the signatures that we're seeing in the LiDAR data. Again, we'll have to do quite a bit of ground truthing here and combine this with, you know, the decades of research that has been done on Delos. But we can already start to see a very different signature in terracing systems and in the rural landscape here versus here. And this is something else entirely, most likely a quarry. For Yaros and Andimilos, initial analysis also shows very different types of land use. We have a pretty extensively terraced landscape in eastern Yaros on the one hand, alongside modern installations that are there, but we don't know the date of these agricultural systems. On the other hand, in Andimilos, we see a sort of familiar signature from Poliagos. The area of most of Andimilos is too steep for even terraced agriculture. So we suspect it is used mostly for herding. And in fact, this is really interesting based on some other work that has been done on Andimilos related to endemic species of goats there that probably came via Crete at some point in the Neolithic period. At least that's what I think. But you can already make out these signatures of large-scale enclosures over here, smaller ones in these areas, and just a little bit of terracing, maybe to keep a little field alongside the goat herds. As we look ahead to putting these data sets together, some of our quantitative and comparative goals are, as we said, to provide training data and test cases for machine learning. I personally don't want to draw every single one of these terraces myself. It'd be great if we could automate some of that, but in order to do that, we're going to need to start working quite a bit more seriously with the machine learning capacities. We also want to use these data to examine each island and its individual resource base for things like agriculture, pastoralism, and other forms of resource extraction. We can start to quantify some of this with the terraces very easily by investigating the amount of effort invested in the building up of these landscapes and in landscape modification, and also the potential field area that can be harvested from these terraced landscapes and how that changes when you introduce the terraces. And we also want to get in, these can be used to look at island thresholds, island size thresholds for long-term use. So we've started to notice a pattern where larger islands seem to have more consistent habitation and use than others. In general, the settlement evidence is very spotty. Even very small islands can have activity on them, but it tends to be limited to certain periods and to not be continuous. Those gaps of occupation seem to narrow the larger an island gets. But again, we're still in early days of this analysis. And finally, we want to look at questions of relative marginality and connectivity, and these are, of course, chronology dependent. So how do the islands that we're surveying in the context of SCIP fit into larger settlement patterns, and how does this change over time? Poliagos, for example, may have been highly interconnected in the early Bronze Age with the surrounding settlement pattern, but a more isolated stopover spot in the Middle to Late Bronze Age. Finally, there are applications for this data beyond archaeology. We're already collaborating with geomorphologists, as I mentioned, but also we aim to share this data with people from forestry and land management, and there are significant applications for natural and cultural conservation industries. So we hope that that these data can do a lot of good beyond our individual project. So, in conclusion, LiDAR works. I think it's especially useful at regional scale, though. We've seen great application from individual sites, but for me, anyway, the most exciting questions are how do we kind of scale this up into comparative and quantitative analysis. So there's significant value added even when it is looking at an area where systematic field work has been carried out. It just sees things that other people and other sensors don't. LiDAR also offers modes of analysis and levels of detail that are not possible with other methods. But it's important to remember that this is not a cure-all. It does not see everything, and it does not replace other forms of remote sensing, especially at a small scale, where many of the methods that we've been using for a few years now, especially photogrammetry and newer methods like thermography, have a lot to offer. But finally, the biggest point, perhaps, is that layered multi-method approaches to survey both increase efficiency in the quality of data collected, and that these methods are really complementary to each other. It's not an either-or thing. It's how you can combine these to be most useful. So in concluding, I want to thank the National Science Foundation who funded this research. I want to thank certain colleagues who've been very, very involved in it. Tom Garrison from UT Austin and Rosie Campbell, currently at Cambridge. And my colleagues at the effort, Dimitris Athanasoulis and Zosi Papadopoulou, who have been key to this collaboration and will be key to the collaborations moving forward, especially around Delos and Rhenia. Aerial photography and thermography by Hussein Ozturk and Evan Levine, as we mentioned, and the wonderful pottery analysis that you saw here was led by Danica Nenova, also with contributions from Anna Belza and Charles Sturge. Finally, thank you to all of you for your interest and attention.